exponential function is a function that has the form some constant a times a constant b raised to the x power, where x is the variable. So if we're given a bunch of data, how do we look at a data set and determine if, in fact, it's conforming to an exponential function or not? Well, let's take a look and see. So here are a bunch of x values, -1, and then the y values that go along with it, -1, 2, 0, 5, 1, 8, and 2, 11. We can see these are all increasing by 1 each time. So let's see what's happening as we look at the y values. Well, you notice that going from 2 to 5, that's an increase of 3. And then from 5 to 8, that's an increase of 3. 8 to 11, increase of 3. And so what we see is that, in fact, these are actually increasing at a constant difference. So the differences here are constant, increasing at a constant rate. This is linear. This is definitely not exponential, because, in fact, it's linear. So here, this is an example where, in fact, the values are growing not fast enough to have that dramatic growth to make it exponential. In order to actually have exponential growth, what we need are not constant differences, but constant ratios. There's another data set. Let's take a look at this. Again, we see that the x's are increasing by 1. What's happening to the y values? Well, to get from a half to 2, what happens? Well, let's take the ratio. 2 divided by a half, we see is actually 4. What about 8 divided by 2? That's 4. What about 32 divided by 8? That's 4. So we have constant ratios here. That should imply that this thing actually is an exponential function, and in fact you can see that, because in fact if I take this number and multiply by 4, I get this. Take this number, multiply by 4, I get this. Take this number, multiply by 4, and get this. So we can see that we're constantly introducing an extra factor of b, or in this case 4. This is an example of data that seems to be conforming to an exponential function. Let's take a look at another application together. So Bernie the chef measures the temperature of turkey in 5-minute intervals after it's taken out of the oven. And our mission is to write a function that models the given data. So here's the data set. So here's the time intervals. Here's the first time interval, first time, and then 5 minutes later, and then 5 minutes later, and 5 minutes later, and 5 minutes later. And here's the temperature. And now what we would like to do is try to model that. So again, the first thing we try is look at first differences. I'm not going to write it down. I'm going to show it to you here. So over there, we're going to take a look at the first differences, see if it's constant. Let's take a look and see. No, they're not constant. All right, but let's try second differences. Maybe it's actually going to be quadratic. Let's look at the second differences now. Oh, no. All right, so we know that it's probably not going to be a good model fit with a quadratic or a linear. We might want to stop here and think maybe this is a candidate for exponential. So let's take a look at the consecutive ratios. All right, so let's now see what we get here. If we take a look at the first ratio, so 173 divided by 180, what we get is approximately 0.96. Okay? If we look at the next ratio, we see 0.97. If we take a look at the next ratio, we see 0.98. And if we take a look at the last ratio, we see 0.99. Well, these aren't constant, but you have to admit they are pretty stable, pretty close to staying the same. And so, in fact, we might be able to, since it's close to being a constant, we might be able to actually use exponential regression using a graphing calculator to actually figure out what might be a good model for this sideways data. And so, in fact, we could actually try that. So let's see if we can model this. It's not going to be a perfect fit, but maybe it's going to give us enough information about the structure of the data that we want to model this with an exponential regression. So what do? We take the graphing calculator, as we've seen before, and we put in both lists. Okay, we run the exponential regression, and that produces out the coefficients a and b. You can take a look here. You can see exactly what we'd see. What we'd see is, and I'll read that off right from there, what we're told is the calculator reports that A would be 182.79, and B would be 0.98. And so a guess, an estimate that of the exponential function that would capture the spirit of this data set seems to be, well, 182.79 times 0.98, all raised to the x power. And so here's an exponential function that seems to fit reasonably well to this particular turkey temperature data set. Boy, diamonds are very, very, of course, valuable gem. And in fact, we could say a lot about diamonds. This table right here, in fact, gives us the weight, which in diamonds are weighed in carats, and the actual value. And here is what we want to do. We want to find an exponential model for this data, and then use the model to estimate the weight of a diamond that's worth about $6,000. So you can see the table sort of ends right before 5,000, but assuming that this data is going to be modeled with an exponential function, the question is, can we find that function, and then can we use the function to then extrapolate and say what's going on when we have a $6,000 diamond, what would its corresponding weight be? Okay, well, a wonderful way of dealing with this sort of complicated diamonds data is to actually take out a computer or a graphing calculator and actually use it to produce what's called exponential regression in order to figure out what is the exponential function behind the data. So exponential regression means trying to fit the data with an exponential function. So how would you use the graphing calculator to do this? Well, we have the data, and the first thing we do is we enter each of this information, this data, and this data into two lists. So we enter that into two lists, and then we would actually do an exponential regression to get the equation. And so the equation would look like for this data, if you were to plug it through, and I'm doing it there live so you can actually sort of see how it would look for real, but the thing we would get, when I should use a diamond color, or purple, would be that the value, given the weight, would be 935.67 times 1.52 to the W power. Okay, now, where do we go from here? Well, what I want to do now is I want to see when, in fact, what the weight is when this value here, when the value is equal to $6,000. So I want to make this $6,000, and I want to find out what W is going to actually make this equal 6,000. So we've seen this before. What we do is we'll call this W1. So we'll enter this function for W1, and then we'll actually enter the constant function for for Y1. So we call this Y1, this function Y1, and then Y2 on the calculator will be the constant function 6,000. And then we just graph them, and we look for the intersection. Now I want to show you the graph of them. So here is the graph of them. Okay? And then what we want to do is we want to adjust the window to see the point of intersection. And you can see that point of intersection right there. And now we can actually find what the value for W is at that point of intersection. And if you read off there at the screen, you can see it. We see that it's approximately 4.44 carats. And so there's the answer. So you can see the power of the computer actually really allows us to focus in on even diamonds.